Hi, this video deals with a very important topic in geology. In previous videos, we saw a good example of the Earth as a system composed of numerous interacting parts, or subsystems, when we reviewed the historical development of the continental drift hypothesis. We also discussed how continental drift, a hypothesis proposed by Alfred Wegener, will underpin a fundamental unifying theory developed in the second half of the last century, a true scientific revolution, plate tectonics, that arguably could be regarded as the most important development since the inception of geology as a modern science. This video is the first of a series of two dealing with plate tectonics. I hope you enjoy it, and don't forget to like, share, and subscribe. In previous videos, we have remarked that the physical properties used to define the internal zones of the Earth include whether the layer is solid or liquid and how weak or strong it is. It is a function of many things, including both their composition and of the temperature and pressure of their environment. Viewed over long time spans, the rocks of the lithospheres are constantly forming, changing and reforming, as we saw in the video dealing with the rock cycle. I will place the link in the description below. The internal dynamics that power the Earth also show up in the surface and have effects that we can perceive and affect our life, like volcanic eruptions and earthquakes. This video reviews how, following continental drift, the theory of plate tectonics was developed and constitutes a unifying theory that allowed us to explain many observations in the surface and relate them to the processes in the subsurface. Following the proposal of continental drift, the theory of plate tectonics constitutes an integral model of Earth's tectonic processes. At a larger scale, tectonic processes are those that deform the Earth's crust to create major structural features, such as mountains, continents, and ocean basins. Following continental drift, geoscientists, including geophysicists and geochemists, made several revealing discoveries that resurfaced the overall interest in the Earth's internal dynamics and the already existing continental drift hypothesis. By the late 1960s, these developments had led to a true revolution in the understanding of our planet, encompassing more integrated explanations known as the theory of plate tectonics. Following World War II, oceanographers equipped with new marine tools explored the planet's ocean basins and came to the discovery of a global oceanic ridge systems that winds through all the major oceans in a manner similar to the seams on a baseball. As more research was conducted across the ocean basins, geoscientists also noticed the following things. Studies conducted in the Western Pacific demonstrated that earthquakes were occurring at great depths beneath deep ocean trenches. Dredging of the seafloor did not bring up any oceanic crust that was older than 180 million years. Geoscientists thought that sediment accumulations in the deep ocean basins were thousands of meters thick, but they found that the sediment thickness in the ocean basins were much thinner than they had predicted. When all the evidence slowly and painstakingly began to emerge, by the late 1960s, these developments, among others, had led to the unfolding of a far more encompassing theory than continental drift, known as the theory of plate tectonics. The word tectonics comes from the Latin tecto, that means to build. To understand how entire continents can move, we must remember that the lithosphere is rigid, divided in oceanic and continental crust. The composition of both the oceanic and continental crust affect their respective densities. Oceanic crust is composed of rocks that are rich in iron and magnesium, and therefore oceanic lithosphere has a greater density than continental lithosphere. Continental crust, on the other side, is composed largely of less dense rocks, composed mainly of felsic minerals, making the lithosphere less dense than its oceanic counterpart. Underneath the lithosphere lies the asthenosphere. It behaves a bit different. It responds to forces by flowing because with increased depth, the higher temperature makes it more ductile. By contrast, the relatively cool and rigid lithosphere tends to respond to forces acting on it by bending or breaking but not flowing. Because of these differences, Earth's rigid outer shell is effectively detached from the asthenosphere, which allows these layers to move independently. In the second half of the 20th century, as the result of oceanographic exploration, came the discovery of a global oceanic ridge system that winds through all the major oceans in a manner similar to the seams on a baseball. Well, they are part of a bunch of parts of the lithosphere that are broken into about 24 segments of irregular size and shape called lithosphere. lithospheric plates, or simply plates, that are in constant motion with respect to one another. Of those, in terms of their size, 7 plates are giant, the remaining are intermediate and of a smaller scale. However, at this stage, we must say that in addition to the ones shown in the map, several smaller plates have been identified but are not shown here. Let's review them according to their size. Starting off with the giant ones, they make up for 94% of the Earth's surface area. These include the North American, South American, Pacific, African, Eurasian, Australian, Indian, and Antarctic plates. Of those, the giant of giants is this one, the Pacific plate, which encompasses a significant portion of the Pacific basin. The remaining 6 large plates include an entire continent plus a significant amount of ocean floor, like this one for example, the South American plate, that encompasses almost all of South America and about 1/2 of the floor of the South Atlantic. Intermediate-sized plates include the Caribbean, Nazca, Philippine, Arabian, Cocos, Scotia, and the Juan de Fuca plates. These plates, with the exception of the Arabian plate, are composed mostly of oceanic lithosphere, whereas the Arabian plate is composed of continental lithosphere. One of the main tenets of the plate tectonics theory is that plates move as somewhat rigid units relative to all other plates. As plates move, the distance between the plates increase. However, parts of some plates are comparatively soft, such as southern China, which is literally being squeezed as the Indian subcontinent ramped into Asia. Because plates are in constant motion relative to each other, most major interactions among them, and therefore most deformation, occurs along their boundaries. In fact, plate boundaries were first established by plotting the locations of earthquakes and volcanoes. Plates are bounded by 3 distinct types of boundaries, which are differentiated by the type of movement they exhibit. Let's review them in more detail. Divergent plate boundaries, also called constructive margins, are called constructive because they occur where 2 plates move apart from each other, resulting in upwelling of hot material from the mantle to create new seafloor. Convergent plate boundaries, also known as destructive margins, they are called destructive because they occur where 2 plates move together, resulting either in oceanic lithosphere descending beneath an overriding plate, eventually to be reabsorbed into the mantle, or possibly in the collision of 2 continental blocks to create a mountain belt. Transform plate boundaries, also known as conservative margins, they occur where 2 plates grind past each other without the production or destruction of lithosphere. For example, and to illustrate one of these boundaries, the Alps were created by the collision of the African and Eurasian plates, continental collision. Both divergent and convergent plate boundaries each account for about 40% of all plate boundaries, whereas transform faults account for the remaining 20%. The nature and characteristics of each one of the 3 types of plate boundaries will be the topic of our next video. This video deals primarily with the theory of plate tectonics and why it constitutes perhaps the most important unifying theory in earth sciences. We have reviewed in previous videos the continental drift hypothesis and considered the evidence that finally led to the acceptance of its direct descendant, the theory of plate tectonics. As a unifying theory, plate tectonics has implications in the 2 broad subdivisions of geology. These are physical geology and historical geology, as it can be used to explain volcanoes, for example, but also it provides a mechanism to explain how entire land masses have split apart in the past to form our modern continents. That is why we say that it is a unifying theory that encompasses many moving parts at different scales and that is governed by nature laws like gravity and is determined by properties like the density of the minerals and rocks. Thank you for watching up to this point. I hope this video contributes to increase your admiration and amazement towards our planet and its interconnected systems. Please let me know in the comment box which one you think is the most important contribution of the theory of plate tectonics to the understanding of our planet, but more importantly, why? About me? Well, I like how it explained volcanism phenomena such as hotspots, for example. I think that that's pretty cool. And why? Because volcanoes are a sort of windows through where we can see and understand what happens underneath us, below our feet. So they give us a sort of a sneak peek on the internal dynamics of our planet. And you? Please let me know in the comment box and I will do my best to answer all of them. Don't forget to like, share, and subscribe, and I will see you in our next video. Ciao!